Hi, everyone. Welcome. I'm delighted to invite you all today to the post-talk discussion from our monthly colloquium on the inference series. So as you all know, as part of this cross-disciplinary project under trying to understand the nature of inference, looking at correlation and causation, we have a series and we have distinguished speakers who give a lecture. And in the following day, we have a post-doc talk conversation with another distinguished scholar who represents a slightly different point of view, who will speak to the lecturer and answer lots of questions that we might have, and also bring in some additional perspective to the topic of discussion. So before we delve into the discussion, I would like to thank our benefactors, Mr. and Mrs. Richard and Barbara Franke, whose support of this program and many other activities at Yale is gratefully acknowledged. And I also want to remind you once again that we are recording this event, and the recording will be available on our website. And as a result, all participants must mute their videos. And of course, as always, if you wish, please go ahead and start submitting your questions through the chat. And Dr. Kemp and I will, at the end of the conversation, pass on your questions to both our conversants today. So just a quick a reminder that our speaker yesterday was the distinguished philosopher of science, Lorenzo Magnani. Professor Magnani is on the faculty in the Department of Humanities in the philosophy section. And he's also the director of the Computational Philosophy Laboratory at the University of Pavia in Italy. He is truly interdisciplinary in his intellectual interests. He's a philosopher, epistemologist, and cognitive scientist. And he spoke to us yesterday about the power and the limits of scientific models. So we are really fortunate to have as the conversant for our postdoc conversation today, Professor James Weatherall, who is the professor of logic and philosophy of science at the University of California at Irvine. And I'm also delighted to let you know that Jim is one of the core members of our team on this project, trying to understand the nature of inference. So Professor Weatherall has been at UC Irvine, where he's also a member of the Institute for Mathematical Behavioral Sciences and the Center for Cosmology, also another exemplar of true cross-disciplinary scholarship. His most recent book, which is absolutely fabulous, is The Misinformation Age: How False Beliefs Spread, which is co-authored with Kaylin O'Connor, and it explores the social dynamics of belief in evidence-rich environments. And he has another fabulous previous book called Void that was also published. Both these books are published by Yale University Press. And he had an intriguingly titled book, which I have not read. It's called The Physics of Wall Street, which was published as a trade book. So his research interests concern sort of a variety of intellectual issues in the mathematical and conceptual foundations of physics, philosophy of cosmology, and social epistemology. And before I invite them to start conversing, I just wanted to remind you to take a look at our webpage for the Learning by Doing project, and remind you that we have this monthly colloquium series, which will continue through the summer. And our final Franke program event, book talk for the semester, is Linda Lynn Hopt's, who is the author of Mozart Starling, and that's on April 27th at 4 p.m. Okay, without further ado, I would like to invite Lorenzo and Jim to have this conversation that we are waiting to hear and learn from. Thank you so much for coming.
Thank you, Priya.
Thank you, Priya.
So I actually, if you don't mind, I prepared some slides following the model of some of our previous events here, just a few of them. And so I'm gonna go ahead and share this screen here. Okay, can everyone see the?
Yep, great.
Okay, great. So I just wanted to, begin by thanking Professor Magnani for his talk yesterday. It was very stimulating, and I'm going to try to highlight a few features of the talk. I have two sort of big questions that will come up along the way, and which I'll sort of return to at the very end here. Partly, this is a reflection of having been inspired by some of the ideas that Professor Magnani presented yesterday. But partly, I'd also like to get into a little bit more about just what's at stake in some of the issues that were raised yesterday. Just to begin, though, I appreciate that this is an interdisciplinary audience, and so I thought it might be helpful to give a little bit of context for some of the debates that we saw reflected in the talk yesterday. And so to begin here, we're working within a certain historical context in philosophy of science. So philosophy of science as a sort of standalone discipline emerged in the beginning of the 20th century, following work in mathematics and in physics in the late 19th century and early 20th century. Much of the early 20th century work in philosophy of science emphasized the role of theories in science. And there are lots of reasons for this I don't need to get into. But the basic picture was one where theories could be thought of as sets of sentences. They were assertions about the world. They did various sorts of things. That they were understood to make predictions. They were understood to be the sorts of things that could be confirmed or falsified. Eventually, philosophers came around to recognizing that theories could play a role in explanations. The way that they would do this would be by warranting particular inferences. And so explanation and prediction were quite closely connected to one another. And within that context, you had views about what science did, like what it meant for a successful scientific theory to be successful. And so one attitude that people had was a realist attitude, where you would say that a successful scientific theory was one that was true. It makes assertions about the world, and those assertions are true or approximately true. Anti-realists, meanwhile, would say that no, what theories did was they somehow organized relations between possible observations. The theories themselves didn't make true assertions. They were merely perhaps empirically adequate or led to successful predictions without doing more. Okay, but so that's only part of what science is. Maybe, according to some people anyway, a small part of what science is. And during the final third of the 20th century, you began seeing within philosophy of science increasing emphasis on other aspects of scientific practice. And in particular, philosophers began to highlight the fact that formulating, testing, and extracting explanations from theory isn't the whole story. Much of science consists of model-based reasoning. And so to really understand science, one must study not just theories, but also, or even instead, models. But now, within a context where much of the work that had been done so far in philosophy of science had focused on these sort of big questions concerning theories, like what does it mean to confirm a theory? How do theories explain? And are theories true or approximately true? The huge diversity of things that we saw when we started looking into model-based reasoning in science looked odd. It wasn't clear what it would mean, for instance, to say that a model was true or false, or to confirm a model. The kinds of explanations that models seemed to enter into didn't fit into the kind of framework that people had built for thinking about theoretical explanations previously. And perhaps most importantly, or most puzzlingly, models seem to stand in a very different kind of representational relation to the world than people understood theories to, right? Theories were sentences that asserted things about the world. Models seem to have a more semantic character. They look like they were structures of some sort that had some other kind of relationship. And so people began trying to develop ideas about that, right? So how should we think about models, and what does it mean for models to succeed? So you started seeing proposals like models are structures, perhaps abstract structures, mathematical structures, maybe real physical structures that are in some way isomorphic to or partially isomorphic to some part of the world. Or perhaps they're just similar to the world in a way that's not quite as rigid as isomorphism, although also a bit more difficult to try to make precise. It's in that context that people began proposing ideas of a sort that we saw discussed yesterday, like perhaps it's possible that models are representations of imaginary systems that are in some ways analogous to the kinds of imagination that happens in the context of fiction. We also see discussions, and this is not supposed to be an exhaustive list, but the idea that maybe actually models are more like art than like fiction, right? And so Bas van Frossen has defended this idea that we should think of models as representations as we depict the world as having certain kinds of key properties that are captured by the model. And what we see here in these different options is a characteristic philosophical response to looking at a new kind of scientific practice, which is that we need an account. Now, this is the sort of thing that we saw with explanation earlier in the 20th century. We want to say that explanation is part of science. What we need to do is come up with an account of what makes an explanation an adequately scientific one. The idea is to give necessary and sufficient conditions for being an explanation, and then to try to show that all explanations within science have this character. Something similar happened with modeling, with scientific modeling. This sort of in the 1980s, 1990s, even into the 2000s, you started seeing these accounts of modeling, of scientific models, that were presented as attempts to somehow say once and for all what all models were like and how they worked. In the background, there were sort of two big questions you can roughly think of as a metaphysical question and an epistemological question. So one question is, what are scientific models? Are they structured? Are they abstract? Are they concrete? Are they fictions? Are they something else? The sorts of things that I think we saw discussed yesterday. And then something else we saw discussed yesterday, how do scientific models produce knowledge? That's the epistemological question. Okay, so that's the context here. Now, I want to highlight something that I think appeared in Professor Magnani's talk yesterday that seems to me to be right on the money. Something that seems to not be as widely recognized within the philosophy of modeling community as I would like to see, but which I think was on display very nicely yesterday, which is that scientific models are heterogeneous. They're extremely heterogeneous. They seem to enter into lots of different kinds of arguments. They're used for many different sorts of purposes. Professor Magnani pointed to this book that he had co-edited that it was over 1,000 pages of descriptions of different kinds of models and the role that they play in different areas of science that I think just provides a bestiary of the many different kinds of model-based reasoning that you can encounter in science, and which just undermines the idea that we're going to have once and for all some account of what science is like. Now, I'm sorry, scientific models are like. Now, I think that this kind of move towards pluralism is something you see often in philosophy of science, where, someone notices that something is important to science. You start seeing people present accounts that are supposed to describe how that works. And then gradually we realize, no, there's not one account that's going to work for all of the cases under consideration. And so I think that that's a wonderful starting point here to now discussing some of the specifics of what Professor Magnani did yesterday. So I want to fully embrace this idea of heterogeneity, but I want to suggest that there's perhaps a tension between the observation that there's no one model that's going to provide a unified, no one account that's going to provide a unified treatment of all scientific models. And two of the key claims that I took away from Professor Magnani's talk. So he made two very general claims about models. One, that they are not fictions. Now, I'm interpreting this as a claim that no models are fictions. The second is that, and this one, the universal quantifier was very clear in the talk, scientific models are never abstract. They are always concrete. Now, this is one of the two questions. I'll return to it at the end. I'd really like to understand more clearly what is at stake in these claims. In particular, one aspect of Professor Magnani's argument yesterday, which I thought was very nice, was the observation that terms like abstract object and fiction fail to be load-bearing. By which I take it he means that within the scientific discourse, the question of whether or not a particular model is abstract, or the example that he gave us within set theory, set is a load-bearing term, but abstract object isn't. So if you're doing mathematics, you aren't going around trying to determine whether various sets that you might encounter are abstract or not. That doesn't enter into your proofs. It doesn't matter to the sorts of things that you're concerned with doing as a set theorist. Whereas being a set is the sort of thing that matters. And so the idea here is that, as I understood it anyway, and please correct me if I have this wrong, is that abstract object and fiction aren't load-bearing within model-based science. No one is worried when they present a model whether or not it is a fiction. And for that reason, it seems that fiction isn't doing the right kind of thing. We shouldn't have an account of scientific models according to which they're fiction, because being fictions is not load-bearing. But now I want to turn that on its head and ask, if being an abstract isn't load-bearing, what is the alternative? Like, why is it that the alternative is load-bearing? Why should we care about them being concrete? Or alternatively, if being fiction is not load-bearing, what's at stake in saying that they're not fictions? Okay, so we're going to set that aside. That's the first question. The second question is one that sort of builds on some other ideas that Professor Magnani presented, which I found very, as I said at the beginning, inspiring. So Professor Magnani presented a picture of scientific activity as epistemic warfare. Okay? And the idea here is that science is a struggle. It's a struggle for rational knowledge. And it's one where you need to draw on as many weapons or tools or methods that you can, right? You have to be opportunistic. You have to be ready to, do what it takes in order to come up with the knowledge that you need. Now, from this point of view, models are a tool. They're a tool of scientific creativity. He describes them as an epistemic weapon, which are intentionally built and manipulated to the gnosiological claims of increasing scientific knowledge that's not yet available. Now, I think that this picture of science as a struggle is a very nice one. It highlights something that the philosopher of science Howard Stein also wrote about, which is the dialectic character of science. Science isn't a static thing, it's a dynamic thing, and it's a thing that involves lots of back and forth, where scientists advance something, they defend it perhaps even beyond what they have rational justification for, and sometimes that ends up yielding new results that they wouldn't have gotten otherwise, and in other cases it forces retreats where you give up things that you thought you knew. But it's a dynamic and changing process that involves bringing lots of different perspectives and methods to bear. Okay, so let's accept that picture of the scientific enterprise. I want to suggest that there's a front here, a front in the epistemic war, in which philosophy has a role to play. And I want to suggest that that role has to do with the analysis of our methods, and in particular, an attempt to understand, again, using whatever methods we can find, whatever epistemic weapons we can bring to bear, how and why the various aspects of scientific activity that we take to be successful are successful. Now, I want to suggest that there are cases in which doing this, reflecting on how it is that our science is working, can lead to new scientific knowledge through a kind of almost self-consciously philosophical analysis. Now, in many cases, this self-consciously philosophical analysis isn't done by philosophers. Sometimes it's done by mathematicians or by scientists. But it does have a kind of philosophical character, insofar as it involves not just doing science, but asking questions about science. So I want to give an example that I hope will clarify why I'm raising this suggestion. So the example is of the reinterpretation of ether theories in the 19th century. So when James Clerk Maxwell first presented what we now think of as Maxwell's equations, his theory of the electromagnetic field, he included a discussion of the luminiferous ether through which electromagnetic waves were thought to propagate. Now, he actually gives, in his original paper and then revises it over a series of subsequent papers, concrete, specific, I should be concrete here, not in a philosophically loaded sense, I should just say specific mechanical models of how the ether worked, right? And you had this sort of honeycomb pattern of vortices, and these would oscillate or you rotate in different ways, and the other, these little circles will move around the vortices. And this is how electromagnetic waves would propagate, how they'd respond to charges. And the idea was that you can give a mechanical account of, for instance, energy transfer in an electromagnetic field and the propagation of electric and magnetic fields due to charge and currents. Now, Maxwell's accounts here turned out to be inadequate in various ways, but there was a major push within 19th century science to identify alternatives. So other mechanical models that would reproduce the same sorts of qualitative features of the electromagnetic field. Throughout this tradition, there was a sincere belief that there was an ether that the ether had specific mechanical properties, and that the goal of this modeling activity was to accurately represent the details of these concrete physical systems. Now, towards the end of the 19th century, in fact, the early 20th century, the mathematician and physicist Henri Poincaré, responding to a long history of new ether models, but also experimental evidence that didn't support these specific ether models in the way that some of their advocates hoped. He proposed a different way of understanding what Maxwell's models were doing. What he suggested was that Maxwell shouldn't be interpreted as giving a mechanical explanation. This is the quote: "Maxwell does not give a mechanical explanation of electricity and of magnetism." He restricts himself to demonstrating that that explanation is possible. And so what I see Poincaré doing here is shifting from thinking of ether models as the sorts of things that are intended to accurately represent a concrete physical system, to rather something that plays a different role, a kind of how possibly role, right? So you aren't trying to represent a real physical system. You're trying to represent a fictional physical system. Who cares if this is a real system? And in fact, the point isn't to try to say anything about what the actual ether is like, if there even is an ether. The point now is to establish certain kinds of consistency relations, to show that energy and momentum are related to electric and magnetic fields in the right sorts of ways to fit together as a coherent physical system, irrespective of whether the ether itself actually has any of the mechanical properties represented by these models. This was part of a general shift in the late 19th century from thinking of Maxwell's theory as a mechanical theory of perturbations of the ether to thinking of it as a system of equations with certain phenomenological properties and making certain kinds of experimental predictions. And this was a stepping stone to special relativity, because what Einstein ultimately was interested in is how can you understand Maxwell's equations in a way that doesn't require the ether. Now, it seems to me as if Poincaré's self-consciously philosophical analysis of what role models were playing in Maxwell and subsequent work on Maxwell's theory allowed Einstein, so this was a stepping stone in that it allowed Einstein to reconceive of the electromagnetic field in a novel way. But part of that involved drawing a distinction about the role that models were playing, where you went from thinking of the model as representing a real system to a model as representing a fictional system. Now, I want to suggest that there's something important happening here, where we aren't thinking about an account of models. We aren't saying all models are fictions, but rather what we're doing is we're looking at a specific case and we're saying that within that context, it's useful to be able to draw a distinction between different ways in which a model might be doing its representational work. And in this particular case, I want to suggest one of the ways is as accurate representation, something like isomorphism to the world. And in the other case, it's as a fiction, where the point is to establish that certain sorts of relations are consistent with one another, whether this actually has any particular relationship to the actual world or not. I want to suggest that something similar happens when we talk about concrete or abstract objects. You might think that the question, are all models abstract objects, isn't a load-bearing term, right? This was suggested yesterday. I'm totally sympathetic to that, as at that level of abstraction. I also think, though, that there are really useful distinctions that can be drawn in particular cases between models that are more concrete and models that are more abstract, and that distinguishing between those is itself an example of an epistemic weapon that we can use as part of our methodological reflection on the practice of science. And so I have here examples of two ways of studying fluid flows. One is to set up wind tunnels with concrete, actually physical objects that are shrunken down versions of the sorts of objects whose properties under fluid flow we're interested in studying, right? Like a plane in a wind tunnel. And the alternative of studying the same kind of problem by trying to find solutions to the Navier-Stokes equations. And I suggest that the latter is far more abstract, right? I mean, drawing a distinction between the experimental, physical model approach and the abstract mathematical approach seems to me to be a key methodological insight here, and one that you I think lose if you try to say that all models are concrete, not abstract in every relevant sense. Okay, and so this leads to my two questions that I want to lead off with here. And the first is, as I said before, if we're to think of abstract object and fiction as not load-bearing terms, then I wonder what we gain by denying that models are abstract and fictions. Why does saying that models are concrete bear a load if denying that models are concrete does not bear a load? That's the first question. And the second one is, I wonder, and this is really just an invitation to say more, whether you see any positive epistemic roles for some of the doctrines that you argued against in your talk, such as fictionalism. And so do you think that there are contexts where emphasizing the analogies between at least some models and fictions can turn out to be fruitful? Similarly, what about distinguishing between more or less abstract models as a way perhaps of understanding what the different epistemic benefits of these different kinds of modeling practices might be? Okay, and that's the end of the slides that I prepared.
Great, thanks, Jim. So Lorenzo, did you want to tackle that sort of two questions? I think he's muted still.
Yeah, I'm asking him to unmute.
Sorry.
There he is.
Yeah.
Sorry. So thank you for your very rich and stimulating comment to my presentation, and also about other things. So to answer your question, I have to start from the first part of your comment to explain that the birth of the interest about model is related to the fact that during the last century, the epistemological interest in science, but also the self-image of scientists about science, was mainly devoted to its structure, its static structure. So when the interest about models arises, this interest is ambiguous at the beginnings, because on one part it is related to see models in a static way. So you have a theory, you said the interest was in theories, you have a theory, you have a textbook, and there are models that are part of this theory. On the other side, the interest in models is related to the fact that the post-positivist philosophy of science, that is Popper, Kuhn, Lakatos, Feyerabend, emphasized the dynamic of scientific knowledge. And so people discovered that models are an important part of the process of scientific discovery. Indeed, yesterday I said, I think that the most important aspect of models in science is related to scientific discovery. So you proposed, so this is a kind of an historical explanation of the new interest in models that we faced in the last part of the last century. So you also say that you agree, I think that you agree with me, that models are extremely heterogeneous, so we cannot have a unified models of them. But you also say that the idea of epistemic warfare can make room also to a new role of epistemology. And I think that we can show some aspects of this new role. For instance, to indicate, you said, the method that we have to use, but for instance, also some basic aspect. Yesterday, I said discoverability is a problem. For instance, in a recent paper in the British Journal of the Philosophy of Science, there is a research in which the authors are examining how different degrees of connectedness of scientists impact their efficiency in knowledge acquisition. And the results they find suggest that whether and to what extent the degree of connectedness of a scientific community impacts its efficiency in a highly context-dependent matter, since different conditions dim different results. So this is an interesting result because we can see in this case that connectedness is strongly related to the context. So me too, I think that the context in which scientific research is occurring is important. For instance, I think, also taking advantage of my studies about abduction, that what I call maximization of eco-cognitive openness is extremely important in science, in scientific discovery. So you cannot have what I call locked strategies. So, and in this sense, for instance, when you see some areas of science in which there is an excess of patenting and so on, so knowledge is no more in motion. So this is exactly the contrary of the epocality of modern science. But, so I totally agree with you when you pointed out this problem of making epistemology in a new perspective, as a part of epistemic warfare. So this is an idea that I totally agree. Now, there is the problem that is related also to your explicit question that I said, and fiction, abstractness, concreteness, and so on. So I said, models are never abstract because they are always concrete. So you say also concrete is not a load-bearing predicate. Okay, the problem is that in my case, I am adopting an epistemological perspective that is strongly related to cognitive science. So when I see a concrete object, I see a concrete object object not in a philosophical sense, but adopting a kind of a scientific view. It is a result of science that if you have a mental image, this is a concrete physical and biological event. When you write a proof in a sheet of paper, this is a concrete object. So I prefer to adopt this idea of concrete objects because they are in tune with the recent result of cognitive science, for instance, about distributed cognition, extended mind, embodied mind. So the results that emphasize the interplay between internal representation and external representation. But as I said, I also said that
Lorenzo, I just had a quick question. I was just wondering, where does sort of serendipity fit in this sort of serendipitous discoveries, right? So where does that fit into this rubric when we are talking about sort of, extended mind and...
Okay. So do you remember when I presented that example taken from ethnographic research of Nersessian and Chandrasekhara? So you see, in that case, two concrete models, an in vitro models and a computational model of the same situation that, thanks to the fact that you manipulate the model and you internalize the model, the intertwine between internal and external relationships is the producer of something new. So in this case, but to come back to James' observations, of course, we can still use the adjective abstract because, of course, there are differences. I said yesterday, they are abstract in a pequeña sense, because they are always concrete objects from a cognitive science point of view. If you adopt a naturalistic perspective about these things, in which you for instance, you said, what are scientific models? This is not an interesting question because it is old-fashioned, it is pre-Kantian, as I said yesterday. So this is my answer, that I think that avoid some parts of the old lexicon about scientific discovery is more in tune with the possibility of managing a novel epistemological view of science. So if you use the term fiction is intended not as a falsity, is intended as a character of a romance, like Anna Karenina. I do not think that it is good, that is productive to use that term. But of course, you can also use it in some historical analysis, but I would prefer to avoid, to transform the epistemology of model-based reasoning in a kind of, let me say, empty dialectics between journal papers in which there is a John that says, in my opinion, fiction is ABC. Then Mario arrives and say, no, I think that there is also the situation E. And then there is Elizabeth that says, okay, but in this case, because in this case, I think that we are trapped in a kind of scholastic, not in the sense of medieval scholastic, not in the sense of the philosophy of neo-scholastic, but in the sense something pedantic and something, as for instance Daniel Dennett says in a bit aggressive way, I have to say, to produce a philosophical proliferation of papers, he says, characterized by abiding insignificance. So it is terrible. So, but I would prefer to avoid to see the destiny of epistemology as a kind of struggle of micro niches, micro academic niches. And I think that fiction is itself is also acceptable, but fictionalism opened the door of this kind of making epistemology, philosophy, that I have to be sincere, I do not like so much. Mm-hmm. So I think that I was able to answer almost everything, because consider also that the concept of fiction, for instance, there is this observation, this is my last counter observation, of an author called Levy, that correctly say that the concept of fiction derives from Walton's view of make-believe, the idea of make-believe. But he says, in Walton's view, fiction are intended as a set of utterances produced in order to get, make believe, that is, fiction are intended something like some promoters of rule-based practices. But Levy says, in reality, fictions in literature are strongly related to the authors and their intentions, treating interpretation as a near cousin of the practices we employ in everyday communication. That is with natural language. That is the literary language of romances, of course, is related to everyday language. So this is not the case of the epistemic warfare. So fiction, also from this perspective, is not particularly adequate, because it is related to the everyday communication. And the intention of the author when invents a fiction is to promote an imagination in the audience. They are directed by the authors, okay? So these are my observations about your notice that I appreciated a lot. I think that, okay, of course, you said, are fiction fruitful? Why not? You can use fictions, but when you make an example like yours about Maxwell, Poincaré, and Einstein, but not in the case of a kind of a struggles between an academic micro niche.
So I just want to sort of draw out a few things. So first, it seems to me as if there's sort of a few different levels going on here. One is that, so for instance, when you say that models are never abstract, in part what you're doing is highlighting a background commitment to physicalism and a kind of cognitive science attitude towards how to think about scientific practice. And so, in some sense, tell me if this is wrong, it sounds like you're denying the existence of abstract objects in this sort of broadly Platonic sense altogether, which is fine, right? I mean, so that's just how, mathematical objects are also things that are realized as particular configurations of neurons and, are shared in complex ways. And that's compatible with, nonetheless, pointing to examples of actual scientific practice and saying, well, this kind of modeling does seem to be using a different kind of structure than this other kind of modeling. Drawing distinctions in that context makes sense. I mean, I take it. Does that, I mean, we can still say that numbers are different from chairs, even though it's not the case that numbers are not themselves the sorts of things that are exist independently of abstract in this particular sense that you're rejecting. Does that sound right?
Okay, but I agree with you. So
good.
The problem is that also in mathematics, always you have to deal with something written. So there is this interplay between written things and the internalization. So the same happens also in religion in some sense, because the sacred texts are written, so they have to be something not only spiritual, And if you approach scientific discovery, in this case, mathematical discovery, of course, you can use the adjective abstract. It is good, but you also have to check what happens, for instance, in proofs, in written proofs, and not only from the propositional and symbolic points of view, but also from the point of view of their iconic shapes. Because when I was able to talk with some mathematicians, and they said, when we are dealing with a proof, we also see the shape of the proof. That is something visual, something iconic, that, of course, it is an externality, concrete, that affords something new in the mind, because you re-represent what you have manipulated outside to reach new affordances. So this also happens in the case of mathematics. I showed the example of Lobachevsky because Lobachevsky was still using geometrical diagrams, like in the elementary mathematics, the Euclidean mathematics. In that case, the diagram was completely important, but also in modern mathematics that doesn't use diagrams, there is the problem of proofs, also in logic. And in this case, you have abstract objects, but you have to see also the way in which they are really existent in concrete objects. By the way, a last observation. Leibniz used the expression fiction, fiction in French, because Leibniz invented, together with Newton, the infinitesimal calculus, the differential, the x. But he immediately discovered that the x doesn't exist. Is wonderful for making a calculation, but you cannot find in the set of the real numbers the infinitesimal. And he called fiction bien fondée, that is something that doesn't exist, but that is able to, in this case, you can use, this is a smart use on the part of Leibniz. And you know that in the 60s of the last century, Abraham Robinson built the non-standard analysis, in which there are infinitesimal and infinite numbers, and so the infinitesimal is no more a fiction in non-standard analysis. So this is a case in which the Leibnizian use of the word fiction was clear and bien fondé. Fiction bien fondé, and also Leibniz's observation was bien fondé.
So yeah, that is a useful clarification that I didn't know that the fiction originated from sort of Leibniz, but that explains why you cannot use it to mean either falsity or imaginary, right? That you cannot.
Okay.
Okay.
Okay, consider that Leibniz, of course, used the fiction. Fictions or fiction, the word fiction also derives from Latin, okay? But the main meaning of fingere in Latin is fingere exactly like in Italian. The main meaning, the first meaning, and also I make a research on this aspect, and also in 15th century English in England, the first meaning was to shape, to form, to build. It is only a secondary meaning, the one that is related to romance, to characters in a play, and so on. So there is also this ambiguity, In the case of Leibniz, fiction was used in epistemological good sense as a falsity, as something that doesn't have a reference. So it was not used equating it to a character, literary character, Anna Karenina, the usual Anna Karenina, or Harry Potter.
Yes. Okay, thank you. At this point, Jim, if you had any sort of follow-up questions, please go ahead. Otherwise, we can also open up. I think we have the chat open. I don't see any questions yet, but meanwhile, feel free to follow up, Jim, with.
Yes.
Yeah, I mean, so I'm curious. So there's something when we talk about mathematical objects, and this is going a little bit afield of the specific issues addressed in the talk, and sort of highlighting some of these, responding to some of these sort of background ideas that we've just been discussing. There's a sense in which the many different concrete in your sense, right, of sort of specific mental realizations, in brain states, right, of mathematical things, share something with one another, right? And as a mathematician, you would think of this as there being different concrete representations of what mathematicians would call an abstract thing, right? So in the context of group theory, for instance, you would have many different representations of the abstract group. Abstract here being used in a mathematical sense, not in a metaphysical sense. But I wonder, though, how to understand that same kind of relationship. So for instance, your concrete representation of set and my concrete representation of set presumably share some properties. They don't seem to need to share their physical properties. I presume that our brains are distinct, number one, but also number two, that the concept would be realized quite differently physically in different people, and yet nonetheless there's something that they share. And that idea of the something that they share is often what people have in mind when they talk about what the abstract object is. Now, I think that you can talk about that in a fairly non-metaphysically loaded way, okay. But I'm curious how you think about it.
Okay, so I think that if you are a mathematician, you can write something and you can show this object only because you wrote something, so you can communicate, because it is more difficult to communicate something that is not externalized. And you can see what another mathematician wrote, and you can see similarities, for instance, and you can arrive together to share what I called in the presentation yesterday a manifest model. So something that it is shared, and then and that can be the basis of further ideas. But something similar happens also in the case of natural language, because only with the speech it is impossible to build a shared language. You also need a kind of written language, then can be also a tool for communication. So this is a way, the externalization is also a way, a method for the collective enterprise in science. In the case of natural language, is of course building the written natural language is a way of communicate in general way among new human beings. And also you find the possibility of scaffolding your thoughts with written natural language, because only speech, the speech of the primitives, is not sufficient. They are blah, 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 blah. So you do not have a syntactic language like sapiens has. In the case of mathematics, you can see something similar. In the case, it is necessary to share a research and to build some results that are collectives. If you are a genius and you are alone, you can write and continue the interplay with your externalization in a blackboard, in a sheet of paper, using a computer and so on.
So you see, it sounds like you don't think then. So if I have, let's talk about a specific model, one that you mentioned yesterday, the Lotka-Volterra model. Okay, these are just some couple differential equations describing predator-prey relations. I go and I do my analysis of them. I come up with some solutions, and I consider how populations of predators and prey interact. You go and do the same. It sounds like there's not a sense on your view in which you and I have both analyzed the same model, because I've got my internal representation and I've written things down and I've made particular marks on my page, and all of that are those are the concrete things that you want to say are the model. You've done yours as well. You've come up with different concrete internal representations and concrete external ones. But it seems to me as if there really ought to be some strong sense in which we've studied the same thing. And I'm trying to understand. It seems to me like maybe you're sort of even more strongly committed to the non-existence of abstract objects than I would want to be, because I want to maintain that there's some sense, at least, in which, even if I don't believe in, say, Platonic forms, nonetheless, there's something that we have both done. We have both analyzed the same model.
Okay, so in the case of the Lotka-Volterra equations, the problem is that it was not necessary a kind of process of a collective discovery. They were so able to build immediately those equations that they were the fortunate model immediately. So there was not this problem. But imagine, for instance, the case of the discovery of non-Euclidean geometries that I know. There was 2,000 years of speculations and drawings about the fifth postulate of the parallel lines. So for Lobachevsky, Bernard, Riemann, Gauss, and others, there were already available a lot of externalized objects, and they finally found the final manifest model that suddenly became the discovery of non-Euclidean geometries. And it was, in the case of Lobachevsky, the depiction of the postulate was not dissimilar from the depiction of the parallel postulates made, for instance, by Saccheri and other geometers that were stopped. They were not able to see something new, okay? And in this case, you finally arrive to a discovery that you can share thanks to the fact that you worked with with similar drawings, similar images, externalized, of course, because I told you in this case it is a fortunate case in mathematics, because until the 19th century, the mathematicians still used Euclidean diagrams. So very strong externalized objects. Also Euler and other mathematicians. Do you agree with this idea?
Well, I see I see that there was a long process of discovery here.
Very long, 2,000 years.
Yes,
Right.
and that it was a collective activity. What I'm not sure of is whether I would agree that. So it seems to me as if a perfectly reasonable way of characterizing this situation was that you had a group of people who were trying to determine whether or not two things. One, Euclid's other axioms implied, using particular pretty well defined logical operations, implied the fifth postulate. And the other side of that, whether or not this particular intended model, and now in the mathematical sense of model, of Euclid's axioms, was the unique model of Euclid's axioms without the fifth postulate, which of course from the 19th century logical point of view, we now understand to be the same question, right? If the other axioms do imply the fifth postulate, the parallel postulate, then it would turn out that every model in the mathematical sense would have to realize that. If not, then there would be, what we now know are non-Euclidean geometries. It seems to me as if I'm more inclined to think that the parallel postulate never followed from the other axioms, that this was something that was true in Euclid's day. We didn't know it, and Euclid didn't know it. It wasn't something that was only became true through some process of sharing diagrams and collective activity. That was the process by which we worked out this consequence. But this is, I'm not sure to what extent it's just a matter of speaking, that I want to say, there's this thing, the Euclidean plane, where the parallel postulate is true, but where there are also these other things like the hyperbolic plane, where the parallel postulate is false, but where all of the other axioms of Euclid's geometry are true. And that was as much the case when Euclid was working as it was when people finally, when Lobachevsky finally did his work.
Yes, I agree. Consider that for 2000 years, they thought that the fifth postulate was a problem, an anomaly, But the discovery of the new Euclidean geometries concluded that the fifth postulate is okay. Is a good postulate. The problem is that there are also other possibilities. But for instance, also a researcher exactly of my university discovered a lot of theorems of non-Euclidean geometry. The name is Saccheri, Gerolamo Saccheri, but he absolutely was not aware of this fact. And he eliminated these theorems because he considered them contradictory, and he said, okay, so we have to save the fifth postulate, but he was not able to discover the new geometry. So this is an example of externalized proofs, observation, also philosophical considerations of various kind that constituted the eco-cognitive setting in which Lobachevsky, Riemann, and the others discovered new ideas. And this is of the field of mathematics, in which there is not the problem of empirical confirmation, because it is a priori science. There is not the problem of experimentations, but there is still the problem of what Imre Lakatos called demonstrations and computation. So this dynamic interplay of scientific discovery in mathematics too. Good. This was a very interesting discussion.
I know.
With James and Priya, and also yesterday, when you said that problem of the conditions of possibility of creating and making good models, this is terrible, because it is like to find the condition of possibilities of winning a chess game.
Right.
Okay, but you are right, and James too is right, because it is, in my opinion, the same problem. We have to take care of the eco-cognitive settings in which our contemporary science is located, because with bad eco-cognitive settings, we jeopardize discoverability, even if you are in presence of a genius, because the genius cannot exercise his powers without a good epistemic niche. You can also call it an epistemic niche, taking advantage of the evolutionary new theory of the cognitive niches. This is a kind of epistemic niche in which, as I told you, openness is important. I prepared a book a small book with the title is Discoverability, about and the subtitle is also a bit provocative, the ecological the urgent ecological need of protecting human creativity.
Right.
Okay. That is about this problem.
Yeah. So great. I don't see any questions in the chat, so we should go ahead.
I'm sorry.
Yeah,
you know,
that's all right. I mean, no, I think we're listening, and also it's getting late for you. So this was absolutely wonderful. Thank you both. Thank you, Lorenzo. Thank you so much, Jim, for
thank you
this
to
great
James, to
discussion.
you, and
take care and have a lovely weekend, and see you soon. Yeah, bye.
Absolutely.
Thank you all. Bye.
For the continuation of the
yes, to be continued. Yes.
Thank you again, James, and also Ty and the other people.
Thank you.
And thanks everyone for attending.